Okay, welcome to another Friday seminar devoted to modeling for non-modelers. This week we have Brian Gregor, who is a senior transportation analyst with the Oregon Department of Transportation, and he's going to be talking to us today about a greenhouse gas estimation model that he's been working on for quite some time and is getting a lot of attention both here in Oregon as well as around the country. So I think I'll turn it over to you, and we'll have questions at the end.
Okay, thanks, Kelly. So I'll be talking about GreenSTEP, and I'll, even though this is presentation for non-modelers, I'm going to throw in some graphs because I like graphs, but I'll try to explain them so that they're not mystifying. But it's about the GreenSTEP model, which I built to help with strategic planning for greenhouse gas reduction. So I'll first start off talking about some of the strategic planning challenges facing us for regarding energy for transportation and climate change. Then go into some overview of the GreenSTEP model, why it was built, and some of the overview of it, the features, and then go into some more about some selected features that make it different than some other models, and then finish up with a few applications of it, current applications, and then some next steps. So first with strategic planning challenges regarding energy and climate change. So as I see it, we've got this basic sustainability problem for transportation. Our system uses energy and produces waste. To move around, you have to use energy, and in the process of using that energy to move around, you produce waste. And right now we're using petroleum as the predominant energy source, and it's got a high energy density, it's very portable, so it's an ideal transportation energy source. But we're experiencing problems both on the supply side and the waste side with petroleum. And so on the supply side, you've got reduced supplies. We're nearing peak oil, which means that when production peaks, production following will be less and less. And at the same time, we've got increased world demand. And so these things are coming together to increase the costs and decrease the reliability of petroleum fuels. Now, on the waste side, we got the problem of climate, our climate being destabilized by the buildup of greenhouse gases in the atmosphere. We also have the air pollution that comes from burning petroleum fuels. And then you got water pollution, both the pollution when petroleum is spilled into waterways or the waste runoff from roadways, or maybe more significant or subtle is the acidification of the oceans from the buildup from the dissolving of carbon dioxide in the oceans. So in the long run, petroleum's just not a sustainable energy source for the transportation system. And we've got this problem then, how do we solve this, get to a sustainable transportation system without adversely affecting our economy or livability, because transportation is linked up with our economy and our livability. So there have been some legislative directions related to reducing greenhouse gas emissions over recent years. In 2007, the legislature passed a law that established some goals for reducing greenhouse gas emissions. This is codified in ORS 468. And so basically the goals are to reduce greenhouse gas emissions. This is total emissions, not just from transportation, but reduce greenhouse gas emissions to be 10% below 1990 levels by 2020. And then by 2050, those emissions need to be 75% below 1990 levels. And then the law also established the Global Warming Commission, which is there to coordinate its purpose is to coordinate efforts to reduce greenhouse gas emissions and to provide also education about this. Then a couple of years later, the legislature passed a couple of laws that regarding greenhouse gas emission reduction. They're House Bill 2001 and House Bill 2186. 2001 was the Jobs and Transportation Act, but a part of that included requirements for the Portland metropolitan area and for the Central Lane MPO to engage in scenario planning to reduce greenhouse gas emissions. Now, for the Portland metropolitan area, the requirements go further that Metro has to adopt a scenario that will accomplish reductions, and that scenario has to be implemented by the jurisdictions in the metro area. The requirements for the Eugene-Springfield area don't go as far. They have to do the planning and cooperatively adopt a scenario. But there was a debate in the legislature at the time of whether the requirements should be limited to these MPOs and whether they need to be implemented elsewhere. And so in House Bill 2186, it established that there would be a task force to look into this question further and about what to do in other metropolitan areas. And the task force was convened in the fall of 2009 and looked at the issue, and the results of that was a legislative proposal that came into being in Senate 59, and that did several things. It established that the Oregon Transportation Commission needed to develop a statewide transportation strategy for reducing transportation greenhouse gas emissions. And the participants in the process really felt that we needed that in order to have a context for the whole metropolitan areas, need to know where they fit in that context. It established that the Land Conservation and Development Commission needed to develop targets for all the metro for greenhouse gas reduction from transportation, from light vehicles. It didn't require scenario planning for the metropolitan other than the ones that were already required to do. It also established that ODOT and DOT needed to develop some guidelines for doing this plan, help figure out what they could do to help reduce emissions. So that's a legislative context that drives. Now, to help get a sense of what 75% reduction means, I put together this simple diagram in drive around. In 1990, and so if you're just to accomplish reducing the amount of gallons. Now, So in 1990, we had about 2.8 million persons in Oregon. By 2050, it will be more than double that. So what that means is that fuel use per capita would have to be less than an eighth of the 1990 level. Quarter of the fuel, doubling of the population, an eighth, less than an eighth of the fuel per capita. So from about 570 gallons per person to 68. So big challenge to get there, but it's doable, and our agency has gone through a process of developing a draft for the statewide strategy, a vision to get there. And for light vehicles, we feel like we can achieve that. The difficulty really comes out with freight movements and getting down that much. So now I'll go through some background on the GreenSTEP model, start with a gentle introduction to the model before I get into the more technical stuff. So GreenSTEP, it stands for Greenhouse Gas Strategic Transportation Energy Planning Model. One of those acronyms to make a good sounding name, but it's not necessarily a great acronym. But it gets at the main aspects of what the model's about. It's about greenhouse gases. It's about strategic planning rather than implementation planning, so it's a higher level model. It's also about transportation. It's also about energy, and I'll get more into that. So the work on the model started in 2008 at the request of the Oregon Global Warming Commission, and the chairman of the commission, Angus Duncan, and the subcommittee chair for transportation land use, Eric Lemelson, met with several of us modelers from ODOT and from Metro and from some other agencies, and they laid out, here are all the things that we'd like. It's important to model this, and here's this list of things that we think are important to be included in the model. And it became apparent that the models we had couldn't do all of that, or it would be a lot of work to stitch them all together and to modify them to do all of that for the whole state. So that was the origin of working on the GreenSTEP model. Is it working? Okay. And it started off with developing a statewide model to support the development of a statewide strategy. And but because of the way it's designed, it could support metropolitan level analysis too. So we worked with Metro to modify GreenSTEP so that it could also serve their needs to do scenario planning at the metropolitan level at doing strategic level modeling. So why build a new model? There are plenty of models out there. We've got urban travel demand models that deal with travel at a fairly specific level. We've got our statewide integrated model. Why do a new model? Well, I think a lot of this gets back to what strategic planning is. We're looking out a long ways ahead. We've got a lot of uncertainty about a number of things in the future, and so we've got to deal with those uncertainties, and it's really important to come up with a vision. And where do we want to get to? Just like Metro did with the 2040 vision, what do we want the future to look like to address the problems? And what's a general course to achieve it? Now that's different than planning for implementation, which is more of what's done when a metropolitan area develops a regional transportation plan that says, well, we want to widen this highway here or add this transit line. That is implementing a vision. So developing the vision is something that's long range, and you have to deal with risks and uncertainties that Rick Donnelly talked about in the previous talk. And we need to be able to analyze circumstances that may be very different from today. Fuel costs may be much different. Some travel demand preferences may be different. The technologies that we're using may be different. And then we need to analyze many different scenarios to evaluate the solution space, and to consider risk and uncertainty. So you need a model that you can set up and run fairly quickly. And this is very important for considering uncertainty and risk. There are some other reasons. In the past, the concern with air quality modeling was about criteria air pollutants, the things that harm your health. But criteria air pollutants, your concern is where it's a matter of concentration. So you're looking at what's the pollution in a certain area, and then how does that affect people's health. Now, when you're dealing with greenhouse gas emissions, the place the pollutants are emitted is irrelevant. The effect of those pollutants is global. It doesn't matter whether they're emitted in the Portland area or the Bend area. The effect is the same. So one of the implications of this is that it's important to consider all household travel. It doesn't matter if you're just traveling around the Portland metropolitan area or if you take a trip down to Medford. The effect is the same. And urban travel demand models only model the travel that's occurring in the urban area. Then different aspects of travel demand are important than what we look at in urban travel demand models. Day-to-day travel variation is important because it relates to if you've got electric vehicles or plug-in hybrid electric vehicles. That's important for figuring out, well, what is the amount of travel on electricity versus hydrocarbon fuels. On the other hand, travel times and the routes of travel, things that are important in urban travel modeling, are not that important. I mean, they affect congestion, but as I'll talk about later, congestion is going to become less of a consideration for greenhouse gas emissions. And then we need to be able to model a large number of factors that are missing from standard transportation models, and I'll get into those next. So here's a simple tree of different factors that affect greenhouse gas emissions. And so on the one hand, you have various factors affecting travel demand. You've got population growth. You've got, you could add in there also income. You got vehicle ownership and the factors that affect vehicle ownership. And you've got vehicle use and the factors that affect it. You also have to consider the vehicles themselves and the characteristics of those vehicles, their fuel economy, their ages, their sizes, how they're operated and maintained. There's electric vehicles certainly are a big factor that are going to affect greenhouse gas emissions, and so you have considerations like their efficiency and their range. You've got the carbon intensity of the fuels, and so different types of fuels produce different amounts of greenhouse gases per unit of energy in the fuels. Natural gas produces less greenhouse gas for a given amount of fuel energy than gasoline. And then, of course, on the electricity side, it makes a big difference whether electricity is coming from a coal-fired power plant, or whether it's coming from a natural gas power plant, or whether it comes from wind turbines. And then you've got aspects of how the system is managed, whether you have incident management or other things that affect the smoothness of traffic flow, and significantly the pricing of it. How much does it cost people to travel around? And these things are interconnected. And in modeling, one reason to build models is to keep track of the interconnections, because sometimes things can act in a way that are synergistic, and sometimes they can act in ways that are antagonistic. So you build models to try to keep track of those things. So, for example, vehicle ownership affects vehicle use. People own more vehicles, they tend to drive more. Vehicle system management can affect land use by affecting the travel times, and if you can travel around faster, then you tend to travel farther. System management, it affects land use, and that in turn affects vehicle use. You have vehicle use can affect the market penetration of electric vehicles. Land use also can affect vehicle sizes. If people live in denser areas, they tend to buy smaller vehicles that are more fuel efficient. And vehicle sizes affect market penetration of electric vehicles. So that's just an example of connections, but you have connections woven through these different areas. Now, one aspect that's important to recognize about GreenSTEP, and it's similar to the activity-based models that Ben talked about a few sessions ago, is that the modeling occurs at a individual household level. So what you do is you create a bunch of households that are representative of the set of households you'd expect given your projections about future population, the age distribution of the population, the incomes, and so forth. And there are some benefits of modeling at that level. And one of them is that there are synergistic and antagonistic effects of these different factors. And you can keep track of that at a household level. The other thing, as I said before, is that all household travel is important. It's not to greenhouse gas emissions. It's not just the travel occurring within the city where the household lives. It's their whole travel. And then it's important to consider the equity aspects of policies. And policies and conditions like high fuel prices are going to affect different households differently. And so if you model at a household level, you can say, well, what happens to the lower income households versus the higher income households? How are your policies or other factors affecting them differently? And then finally, by doing the modeling at a household level, it really makes the model scalable so that you can apply it at different levels. So it turned out to be very easy to take the statewide GreenSTEP and convert it so it could work at a metropolitan level. And it was easy because the model operates at the household level. And so I'll just give some examples or try to explain that a bit more. So you've got, for each household you're modeling, you've got a structure of the household. It includes the number of people in the household, the ages of the people in the household, the income of the household. You've got also the location attributes of the household, where they're living. And because land use is an important thing also to keep track of, because it affects the amount of travel that people do. And so what we look at is the density, population density of the I guess you'd call it the neighborhood level, and the design, whether it's in a more mixed-use area or not. And then you have the transportation attributes of the community where the household resides. You've got the road supply, and the key roads are your freeways. The freeways and speeds that you can travel affects the distances that people travel, and then your arterials. And then you also have the transit supply, because the transit supply affects the amount of travel on transit and also then the amount of vehicle travel. And then there are a bunch of other things to consider. Travel demand management programs, whether a household works for an employer that's got a commute options program that can end up with less driving. Whether the people engage in eco-driving. Eco-driving is where you drive. You don't have a lead foot when you drive. You don't accelerate quickly. You don't stop quickly. You drive at a more steady pace. The parking costs that the household face, whether the household participates in car sharing, and the other prices that the household faces. And at the statewide level, one difference between modeling at a statewide level versus metropolitan, at the statewide level, you can't dig into every community. So GreenSTEP draws from likely distributions to establish the characteristics for the households living in the metropolitan area. So if a metropolitan area is more dense, then there'd be a distribution of likely neighborhood densities. And those would tend to be more dense than in a less metropolitan area that had lower overall density. But when we apply GreenSTEP at a metropolitan level, then the planners and modelers can dig in and talk about specific areas or districts of the metropolitan area and say, this is the density that we would be targeting in this district. And then the forecasts then are made at the household level as well. And that includes the vehicle ownership of the household, and the number of vehicles owned, their type, whether auto or light truck, the powertrain, which means whether they're an internal combustion engine or ICE engine, whether they're a hybrid electric vehicle or HEV, whether they're a plug-in hybrid electric vehicle or PHEV, or whether they're a fully electric vehicle or EV. And then the fuel economy of the vehicle, and then the age of the vehicle. And there's a relationship between age and fuel economy. The vehicle miles traveled of the household, and we split that out by vehicle. It's important looking at both the daily average, but also the 95th percentile day travel. That feeds into the electric vehicle model I'll talk about in a minute. And then short distance single occupant vehicle tours, and I'll talk about that as well. That's a way to look at what might happen in the area of future bicycling or the consequences of being able to shift more travel in the future to bicycling or personal electric vehicles like electric bikes or similar types of vehicles that are coming along. And then the fuel and energy use of the household by their vehicle and by the fuel and energy type, the greenhouse gas emissions, and then finally expenditures of the household on fuel and other things related to vehicle ownership. And the differences between the two levels at the statewide level, then we summarize that at a county level and at a metropolitan area level. But when the model is applied, at a metropolitan level, then it's summarized to a finer level of geography, whatever was set up for that model. So now I'll get into a little more of the geekiness to talk about GreenSTEP features that are different for this model, and that I think are interesting about this model. So GreenSTEP uses a household budget to estimate how future costs affect the amount of travel, and there are some challenges with looking at costs. Pricing is an important tool. We want to be able to evaluate pricing. People don't pay the full cost or prices of their travel. When we get in our cars and drive around, we're not paying for the cost to the effects of climate change. We're not paying for health costs related to the pollution from vehicle travel. We're not paying the energy security costs. And so we need to be able to model circumstance, say, what if we did pay the full cost? What would that do? We're also facing the prospect of much higher future fuel prices. So we need to be able to say, what if those prices are higher? But we really don't have a lot of experience with high prices. We had the run-up in the last decade, and then the recession came, and prices went down, and they're going up again. But there's not a long historical period of varying prices that we can draw on to build models. So with the approach, I had tried several different approaches to get at prices. One was to include a variable in the model that predicts household vehicle travel, and it failed badly. It predicted, when I compared the trend in by simulating the price changes that occurred in the last decade, it estimated that the run-up in prices would have had a much bigger effect on the amount of travel, and people didn't adjust their travel that much. And I tried an income approach where I used the prices, increased price to reduce people's income, and that was not sensitive enough. And so then went back to square one and looked at household budgets, looked at the consumer expenditure survey data, and chose to use a household budget approach. And the approach is simple. It basically establishes a budget for households, and if their travel expenses are below that budget, they don't change their travel. If it gets over that budget, they start cutting down to be in the budget. And then there's a transition between those two regimes, so that anticipating that people might look ahead a bit and not wait till they get up to the cliff before they cut down their travel. And so there is evidence that there are household budgets, and this graph shows data from the Consumer Expenditure Survey, and in the solid lines it shows urban households, the dashed are rural households, and it shows that with the black line across the top, that in real dollars there wasn't, for a 25-year period, there wasn't a lot of change in the amount that households paid on average for transportation. Now, it gets more interesting looking at the components. The green is what was spent on vehicle purchases, the red is what's spent on gasoline, and the blue is what's spent on other things like car insurance. And what I think's particularly interesting is you see that rural households spend more or spent more than urban households on gasoline. That's understandable. They drive more because they're located further away from things. But it's interesting that they spent less on those other expenditures, like insurance, than urban households. And what's really interesting is that the gap in the gasoline expenditure is about the same as the gap in the other expenses. So it looks like households have these budgets that they spend on transportation, and that it's a reasonable thing to do to model prices by their effect on budgets. And when I did that, I simulated with the household data set used to estimate the model, the increase in their costs from 2001 to 2008, and simulated that and looked at the effect by income, that it followed the trend in the consumer expenditure survey. The dashed are the consumer expenditure survey. The solid is the simulation with the model, and then the different colors look at different income groups. So it did a fairly good job of simulating what went on in that time period, and so it seemed good enough to go ahead with to use in the model. And one of the reasons why it's important to address this is to address what's called the rebound effect. If you have an increase in fuel economy, you would expect that the price per mile to travel goes down, people are going to travel somewhat more. But at low fuel prices, the rebound effect is very little. Most of the if you have a 10% miles per gallon increase, the fuel use goes down by almost 10%. And the VMT goes up only by a tiny amount. But if fuel prices are high, and this is a test with 4 times the 2001 prices, then the VMT goes up, because relative to lower MPG car, people can travel further. And so this is the rebound effect that we want to capture in the model. For bicycling and personal electric vehicles, there's a challenge here that there aren't lots of bicyclers. I know in the Portland area there's more and more, but around the country there's not a lot of bicyclers, so it's a challenge to model them. But it's really important that we look at that, because they could be a more important mode, but also these small electric motors and batteries could really revolutionize that whole mode of travel and be a bigger collection of that travel mode. So to get at that, the way we do it in GreenSTEP is instead look at potential diversion of single occupant vehicle tours, and model for different households how much travel they do in single occupant vehicle tours, and then do what if you could divert 40% of that travel to these other bicycles and other modes. What would that do? And so just to quickly explain the graph, about 8% of the households, 8% of the household mileage is less than, in SOV tours, less than 5 miles in length. Almost 20% is in SOV tours of 10 miles or length. So you can do what-if analysis. We also need to look at plug-in hybrids and electric vehicles powered by the grid, and that depends on the battery range, but also the vehicles, how people use vehicles. If you travel less each day, you're more an electric vehicle is going to meet your needs more often, and so we and with a plug-in, that day-to-day use depends on how much you're going to pull off your battery versus how much you need to use your gas engine. And you can see here this graph shows that assuming everybody has a plug-in hybrid with 20-mile range, that if they live at lower density, less of their mileage is on electricity than if they live at a higher density. And with electric vehicles, if we assume everybody would buy an electric vehicle if it meets their needs, again, you see a relationship between the range and the proportion of the people and the mileage that could be powered by, taken care of by electric vehicles. So these are some of the connections that are important to get at. Finally, I'll go through these. This one's the geekiest slide, so I'll go through it fastest. We don't look at this level at traffic on different roads and equilibrate it, but we look at it as traffic at different congestion levels and on different parts of the system, freeway or arterial. But it's still important to look at this as an equilibrium. If you improve speeds on the freeways, it's going to pull some traffic from the arterials. If you put prices on freeways, it's going to push people over to arterials. And so as the capacity increases, your average speeds are going to increase as well. Now, one of the considerations, and this is work we asked PSU to do for us, is to look at what are the implications of advanced technology vehicles on the effects that congestion has on emissions. And Alex Bogazzi and Kelly Clifton did some great research on this and came up with methods to calculate it, or model that we folded into GreenSTEP. And the significant implication here is that as vehicles, these are hybrid electrics, as they become more efficient in dealing with congestion, then congestion becomes less and less of an issue for greenhouse gas emissions. With current internal combustion engines, as you're going at slow speeds, your fuel economy drops off. You're sitting at a traffic light, your fuel economy is zero. Your car's just idling. You have stop and go. You got lower fuel economy than if you're moving more quickly. Well, you get a hybrid electric vehicle, it'll shut off at the light. So you don't have those idling losses. It'll recover energy as you're braking. And at the slow speeds, it'll use the electric motor, which is more efficient. And so what we actually get is a reversal that here is at a low congestion efficiency, and this is high freeway lane miles, meaning there'll be faster speeds, and then low freeway lane miles, so you have less efficiency at lower speeds, but you get more efficient engines, and the difference tightens up. You get very efficient systems, and it actually reverses. Congestion is more efficient. So, and that's because on the other end of it, you've got wind loss, you've got friction losses as you're going at higher speeds. So this is very important to keep track of when you're looking at greenhouse gas emissions. Quickly, some applications. We use the model to help the Land Conservation Development Commission develop their targets for metropolitan area greenhouse gas emission reductions from light vehicles. We've used it for our statewide transportation strategy that I mentioned before, and we've modeled almost 200 scenarios, alternative scenarios before we got to figuring out, well, what should the vision be? And the GreenSTEP also produced a number of other performance measures. Here you can see, for example, a comparison of greenhouse gas emissions with the vision versus a reference case versus the 1990 vehicle miles traveled per capita. And then here's the percentage of income spent and owning and operating vehicles, comparing different parts of the state and comparing different scenarios. So we're looking at you can produce a number of different evaluation measures. And then Metro's using GreenSTEP for their climate smart communities scenario planning. In the first phase, they evaluated 144 scenarios, and then they'll be working on whittling those down. And then finally, we just started doing some work on a fuels and vehicles taxation study. As you may be aware, as fuel efficiency increases and we get electric vehicles, transportation revenues, which depend on the gas tax, are going to go down and could be substantial. But then you also have equity considerations, because the effect of travel on the road, it depends on the miles you drive. But as an electric vehicle consumes no fuel, it would pay nothing for the system. So there are equity considerations. So we're using GreenSTEP to estimate the future fuel tax revenues and equity for different scenarios of electric vehicles and plug-ins and such. Next steps, we got several things going on to make GreenSTEP easier to use. PB is helping us with developing an Excel interface to simplify the model use, an installer program to make it simple to install all the components, and then putting the data in a database will make it easier to pull out all the household data. We're completing model documentation, and we need to put together a web page so that people can get at these things. We're adding a housing type model to help allocate households better to density levels, and to assist the Eugene Springfield area as they go into their scenario planning, to assist them with that. So with that, I'll take questions.
Thanks, Brian. So we have time for some questions. I just want to remind you, like I do every week, to use your microphone so the people online can hear.
Can you explain exactly what you mean by a 95th percentile day?
Okay, so if you took every day of the year and took the vehicle and said, how many miles did you drive that vehicle? And you ordered them in from lowest to highest, and you took 95% of them, that would be, and found out what that distance was, that'd be the 95th percentile. It would be like with grades. Yes?
How do you expect that when the fuel price is increased, which travel behavior will be more observable between the reduction of travel itself or the change of mode from vehicle to another, like public transit or the bicycle or what?
Yeah, that's a good question. And we don't specifically model mode choice. Instead, we're modeling what the amount of vehicle travel is. So people will, if you have higher prices, if you have more dense land use, people will travel by vehicle less. But we don't say whether they're going to walk to their destination or get on a bus. We can still model the bus or light rail emissions, because an input to this is what's the service level in revenue miles. So you can just convert that with a fuel efficiency to emissions from those modes. Yes.
Can you talk a bit about how freight traffic is incorporated in the model?
Yeah. It's not fully incorporated into this. We do, for metropolitan areas, truck travel on the roads so we take a forecast of overall truck travel, split it between metropolitan areas to get the amount of vehicle miles traveled by trucks, and then that factors into the consideration of congestion, and then we estimate truck travel times and emissions. But for the statewide transportation strategy, we really had to do something different, and we took the same approach in a way as for households. For households, we don't care whether that household is traveling in Oregon or goes outside Oregon. It's Oregon travel. And for air travel, we looked at it. We didn't do it inside of GreenSTEP. We did it outside. We looked at the whole air trip. You know, it's not just what airplanes are going over Oregon airspace. It's that trip wherever you're going. So we got national data on origin and destination to get at that. Now, with trucks, what we did is we took the freight analysis framework data that is FHWA provides. It gives you movements by commodities for different distances. And our committees debated quite a bit about, well, how do you look at that? Do you look at it, what's the greenhouse gas emissions for getting stuff to Oregon that you consume, or what are the greenhouse gas emissions for exporting stuff from Oregon that other people consume, or do you look at half and half? And we decided to look at it as what are the emissions for the stuff we consume to get it to Oregon. And so we had we could get a distribution of this travel by mode, and then estimate for different modes what is the amount of emissions, and then consider, well, what would more efficient travel do? What would happen if our growth in freight was more of higher value products that had lower weight and therefore could have lower emissions. And so we were trying to capture the whole trip. If something is getting exported from Europe and goes on a boat over to the East Coast and then transported to Oregon, what's all of those emissions? And one of the interesting things we found is that, really, you can't address freight emissions simply by the carriers of freight. You have to deal with the question of how much stuff are we consuming, and so it's freight emissions are a bigger problem than just transportation. They have to be considered in a broader economic context. Yeah.
Did you try and do anything with biodiesel to try and give less of a greenhouse gas penalty for travel with biodiesel? Yes,
and we assumed actually in our reference case that the low carbon fuel standards would be adopted by DEQ, and that out by, I think it's around 2025, that the carbon content of fuels would be reduced by 10%, and that would be because of substitution of biodiesel and such. And then in our vision scenario, we went further and said, well, we'll cut it down another 10%. So we did consider that. Now, biodiesel probably is most important for air travel. Cars can run on electricity, planes can't. And so biological fuels are going to be really important for air travel if we're going to reduce the emissions from that. Yeah, Kelly.
From the web. It says, it seems like another reason that congestion might actually decrease greenhouse gas emissions is that congestion causes people to drive less. Was this phenomenon taken into account with regards to your analysis?
Indirectly. The amount of freeway supply is a variable in the equations to predict vehicle miles traveled. So if you have more freeway supply, the operating variable is that you have higher speeds and people travel faster. If you have less supply, it's more congested, people travel slower, they travel shorter distances. So, but it's not, congestion isn't a direct variable in the equation, but it is kind of taken care of. Yeah, Alex?
In making the transition from statewide to metropolitan, can you maybe touch on one or two most difficult things to address, or like gaps in knowledge that you had in trying to make that transition?
Well, really at the metropolitan level, it'd be good if like transit accessibility was measured on a finer scale. Like so if you live in downtown Portland, you have a different transit accessibility than if you live out at the fringe. But currently the model just takes overall transit supply for the metropolitan area and affects the amount of travel. So that would be a good thing to do. Yeah.
Just with the goal of reducing greenhouse gas emissions by 75%, and I know that's not necessarily all from just transit, but to achieve these goals in transit, I mean, do you need like a lot more density? Like, what is the model kind of showing that we're going to need to do in the future? Is it just more density, more electric vehicles?
So certainly one of the biggest things is we need cleaner vehicles. You know, we need to electrify the vehicle fleet substantially, and we need cleaner power to power it. As far as more density, and correct me, Cindy or Dennis, what I'm understanding from the sensitivity tests that Metro has done is that developing the plans according to what the direction is, that stopping all growth of the urban growth boundary doesn't do much different than just carrying out the 2040 vision. So density is important, but if we're on the course of doing the density that we're already planning on, it accomplishes most of what you need to accomplish. But the real big factor is transit service. The big urban factor is transit service. So we were looking at, for the statewide, looking out to 2050 and having, I think, over 3 times the transit service for the Portland metropolitan area than on a per capita basis. So, and it's a nonlinear effect. You know, a small amount of transit. You can think of it with the interstate system. If the only part of the interstate system that was built was between Salem and Portland, it wouldn't have had nearly the effect on travel versus having a complete freeway system.
I have one more from the web. How much error is involved in predicting the long-range use of technologies that are still developing and could be considered in their infancy compared to the relatively static technology of the combustion engine?
Well, that's one of the big uncertainties, is what is going to happen with technology, and that's why it's a good idea to run do your modeling at different levels, and then it comes down to a judgment call of the decision makers where to balance things out, and then it's going to take an adaptive management approach to this. That's one other aspect of strategic planning. You have to monitor, you have to assess what's happening. Is it going according to the course that you thought it would be on, and what are the implications, and then maybe you need to make some other assumptions.
I think we're out of time today, so let's thank Brian for another great talk. Join us next Friday, where Ann Goodchild, who's a professor at the University of Washington, is going to talk about freight modeling. So see you then.